In this course, we'll be learning how to use computer simulations to model complex systems. But before we dive into simulations, the first steps to system dynamics are articulating the problem, mapping a dynamic hypothesis, and then forming what we call a stock and flow model. And I'm going to discuss each of these three steps in more detail. So articulating the problem sounds simple, but it's actually a very important step to take. You don't want to build a model just for fun, just for the sake of modeling. You want to have a clear question or a clear problem that you're trying to understand. So an example of a problem could be why sweetened beverage consumption has increased so much in recent decades. Another problem that's of interest to me in my research is why policies related to obesity sometimes fail. A lot of times we implement policies that seem very logical on paper, and yet they just don't work in the real world. So I'm interested in using system dynamics models to explore counterintuitive results such as this. Once your problem is well articulated, you want to list all the variables that are relevant to the problem. So if you're studying sweetened beverage consumption, variables might include beverage prices, different sources of sweetened beverages, where students get them from, alternative beverages such as water, and any other factors that you think are relevant to the problem. And then you want to sketch the behavior of key variables over time, particularly your primary outcome like sweetened beverages. Looking at patterns over time is a very crucial step. It's not enough to say that sweetened beverage consumption is high, or obesity is high, or fruit and vegetable consumption is low. You need to look at how these variables have changed over a specific time span. And that's where we use what's known as a reference mode. A reference mode is a simple sketch where you draw patterns in your key variables over a specific time frame. It includes both the patterns that have occurred in the past and the patterns that you expect in the future. Commonly, investigators will sketch both the patterns that they fear will happen in the future and patterns that they hope for in the future. So the figure on this slide represents a hypothetical reference mode for obesity. It shows the increase in obesity that took place from 1980 to 2000, along with the fear that obesity may continue to increase in the future and the hope that it will decline in the future. It's a simple sketch. There's no fancy analysis that goes into a reference mode, but sketching these patterns is very important because the shape of trends over time will give you some insight into the types of feedback loops that are influencing your trends. And that's what's known as a dynamic hypothesis. Once you have a clear sense of your problem and the patterns that you're studying, the next step is to form a hypothesis about the structures that are causing those patterns. And that's what a dynamic hypothesis is. It's really like any scientific hypothesis, except that you're more focused on the overall structure of a system as opposed to any particular variable in the system. A dynamic hypothesis starts out as an abstract idea, it's purely theoretical, and it often changes as you go through the model building process. The next step in this process is creating a causal loop diagram to represent your hypothesis. This figure shows an example of a causal loop diagram. It was developed as part of a system dynamics project that is designed to explore commuter cycling options in Auckland, New Zealand, and simulate different policy options to promote cycling. A causal loop diagram such as this is essentially a large set of causal links that form feedback loops to represent the dynamic hypothesis. So I'm going to explain what some of those terms mean. When I say a causal link, I'm referring to the arrows that link two variables in a model. A causal link is exactly what it sounds like. It's the effect that one variable has on another variable. It represents the relationship that just these two variables would have in a vacuum where nothing else changes. The relationship needs to be causal. It's not enough for the variables to be correlated with each other. So for example, if a person consumes more carbohydrates, then by definition, they're consuming more calories, a higher energy intake. Now that's different from saying that carbohydrates cause obesity. It's only saying that if the first variable changes and everything else is held constant, then the second variable will change in a very clear direction. And the direction of that link is very important. Links can be positive or negative, but it needs to be clear which one. It needs to be clear whether an increase in the first variable will cause the second variable to go up or go down. If there's any ambiguity about the direction, then those two variables probably shouldn't be linked together. They should be broken up into a longer causal chain. A causal link is an individual relationship between two variables, but when you have a series of causal links that form a closed loop, that's what's known as a feedback loop. I've already used bike share programs as an example of a feedback loop. As I described earlier, bike share programs illustrate how the environment shapes our behavior and vice versa. And this creates a closed loop that I've drawn out here in which bike share stations increase opportunities for biking, which increases the number of bikers, which increases a city's infrastructure to support biking, which creates even more opportunities for biking. Now, this is an example of what we would call a positive feedback loop. Feedback loops can be either positive or negative based on the polarity of all the individual links within the loop. And as we'll discuss, positive feedback loops produce very different patterns from negative feedback loops. A positive feedback loop is a feedback loop in which there are either 0 negative links or an even number of negative links. So a loop that has 4 negative links would still be considered a positive loop. In a positive loop, variables reinforce and amplify each other. And that's why positive loops, they're also referred to as reinforcing loops, which is what the R in the middle of the loop in the previous slide stood for. These loops tend to produce either exponential growth or exponential decline. For example, a great example of a positive loop is money in the bank that grows through interest. You know, when you increase your savings, the amount that you earn from interest will increase. So that's one positive link. And then the increased interest will further add to your savings. So that's another positive link. And this combination causes my savings to grow at a steeper and steeper rate over time. You know, this is why my mother told me to save money at a young age. I probably should have listened to her more, because as savings grow over time through interest, a small amount of money at a young age can turn into a much larger amount of money 25 years later because of how positive feedback loops like this work. On the flip side, a negative feedback loop is a loop in which there are an odd number of negative causal links. Negative feedback loops are also known as balancing loops because the variables balance or correct each other. They tend to keep a system in a steady state as it converges onto some equilibrium point. And for me, a perfect example of this comes from running, which is one of my favorite hobbies. You know, when I start to run, my energy level's high, and high energy will increase my speed. So that's a positive link. But as I speed up, my energy level drops, so that creates a negative link. And overall, this combination creates a negative balancing loop that converges toward an equilibrium point. In this figure, even when my speed is increasing, the rate of change is getting smaller and smaller over time. And that's the key difference between how a negative loop behaves compared to how a positive loop behaves. In a positive loop, the rate of change is increasing over time. Here, it's getting smaller and smaller. You know, I can't get faster and faster over time. Instead, my speed increases at a slower and slower rate. And that equilibrium point that it converges onto would be my natural running speed, which tends to remain steady for a little while at least. I usually crash at some point during a run. So these are examples of individual feedback loops. A causal loop diagram typically consists of many feedback loops that overlap and intersect each other. As I said earlier, though, a causal loop diagram is very abstract and theoretical. The next step is to translate the causal loop diagram into what's known as a stock and flow model. You take all the ideas in your causal loop diagram, but you express them in what we call stocks and flows, which are much more concrete and mathematical. Stocks and flows represent the movement of concrete entities, such as materials or people or information. This could include the flow of energy through the human body, or the movement of commodities in the food supply, or the flow of people in between different weight status categories. These are all things that can be quantified in some way, and they're dynamic. They don't remain constant over time. You often hear a bathtub used as a metaphor in system dynamics models. The water in the tub is like a stock because it's something concrete that you can measure and you can accumulate, and it can rise and fall at different levels. The faucet and the drain of a tub represent flows because they're the way in which water enters the tub and how it exits the tub, causing the stock of water to rise and fall. The images on this slide all represent other stocks and flows. The rectangular boxes always represent stocks. In this case, the stocks are population, money in the bank, and body mass. The flows going into and out of the stocks, the arrows going into and out of the stocks represent inflows and outflows. Flows have valve symbols because, like I said, they're like the faucet and drain of a bathtub. They represent the way that stocks grow and shrink. Population grows through births and declines through deaths. Money in the bank grows through saving and then it declines through spending. And body mass grows through energy intake and it declines through energy expenditure. In each of these cases, stocks represent something that accumulates over time and can be quantified in specific units, such as people or dollars or pounds. Stocks accumulate over time, but they can also be measured at any single point in time. And that's really the main thing that distinguishes stocks from flows. Let's just say you could freeze time and take a picture of the world. Stocks would be the things that you could measure. A perfect example is obesity prevalence, because prevalence represents the number of cases of obesity that exist at a specific time. Stocks are also straightforward because they can only change through inflows and outflows, through the faucet or through the drain. Flows are a little bit different in a couple of ways. The first is that they're measured in units per time because they represent rates of change over time. Rather than representing obesity prevalence, for example, a flow could represent the incidence of obesity, or the number of new cases of obesity that develop per year. And because they represent rates of change over time, they can't be measured at a single point in time, like stocks can. Flows are also different because they can change due to many things. A stock itself can change the flow. In the case of money in the bank, for example, if you invest your money stock at a constant interest rate, then the more money you have in the bank, the more money you will earn per week or per month or per year. So that inflow is going to increase as the stock increases. And flows can also change due to other variables in the model, which we'll be discussing later on. So going back to the examples that I gave earlier, I should explain what these cloud symbols mean. When an outflow leaves a stock, it could do different things. It can potentially lead into another stock, but it can also end with a cloud symbol, as all of these outflows here do. The cloud essentially means that the units are leaving the system and going somewhere that just doesn't concern you. It doesn't mean that the units disappear entirely, just that they're not an important part of the system that you're trying to model. So again, take the example of money. If you want to develop a system dynamics model to track my finances, then the stock will deplete if I spend money, but it doesn't necessarily matter where I spend it. So if I take my money and I go buy a latte at the local coffee shop, then my money still exists, but it's now with the coffee shop, and I don't particularly care what the coffee shop does with my money. So that's all the cloud symbols represent. It means the stock units are going somewhere that you just don't need to worry about. So those are all individual stocks and flows. A full system dynamics model will typically include multiple stocks and flows that are connected to each other in some way, creating multiple feedback loops. And in the next section, we'll dive deeper into the process of building a more complex model.